series of small components would best represent a large fuel would be very valuable, because then we can start from a smaller, more manageable data set, and also be able to still preserve a lot of the chemistry, because we're going through those pathways anyways. And so with that, I want to be able to look at global statistics of how these fuels decompose, almost come up with a recipe for if you see these particular structures, this is the correct formula to represent it for a fuel mixture. And then one of the first applications I think would be really valuable is looking at jet fuels and propellants. There's quite a bit of active calls for proposals, especially through the Air Force Office of Scientific Research, for jet and propellant type chemistry. So I think this would be a natural fit within that program. For a first start, since we have to do a whole host of different fuels, let's start with one. We can start with jet fuels and start from there. Though it could still be applied biodiesel components, things like that, and go to other funding sources. Another area that really needs improvement is that small molecule set. Like I said, there are errors, there is missing chemistry, there are problems. So especially within the NOx and fuel nitrogen subset, SOx kinetics, which in a lot of cases are completely ignored, and then even some of the smaller hydrocarbon oxygen type reactions. So with this, one idea I have is actually to build a better, more robust, high-pressure natural gas syngas mechanism, where we can look at, we can improve the NOx set, we can improve the SOx set, so we can get emissions on top of just ignition or heat release. And something like that is very applicable to industry partners, Siemens, GE, natural gas turbine companies who need to design new turbines to meet these very strict requirements in terms of emissions. And also something like this would be very applicable to the ACS Petroleum Research Fund, the new investigator startup grant, who are very interested in emissions also. But if I'm looking towards the future, where do I see this going? If you had the chemical composition of a real fuel, if you had the 20 components that you're interested in biodiesel, and the conditions that you want to operate on, I can see eventually, as we start building statistics on how fuels break down, you can use these molecular dynamics approaches and come up with a recipe where you can identify what the ideal surrogate fuel mixture for that particular fuel is, and get a simplified starting point. Also, as we expand and make a more robust base chemistry set, if you combine these two together and put it into a code that can actually use chemical intuitive thinking almost, using something like the reaction mechanism generator type approaches, where you use bond additivity groups to estimate rate constants. So you can bridge from that surrogate fuel mixture to your expanded base chemistry. You eventually could, in theory, completely automate your mechanism generation. So you could plug in your chemical composition, you have this already really reliable, you plug it into your code, it fills in the blanks, and all of a sudden you have a kinetic model that is robust, that has all the reactions for rate constant thermochemistry for everything. And then, so these are going to be very, very large models, but then you could take this and say, all right, I've done this for biodiesel. I now have a kinetic model I can trust reliably for biodiesel. I want to look specifically at NOx formation. And then I can reduce the model specifically for a single target and have it be small enough to be incorporated into something like CFD codes for real-world applications. Or I can look at overall trends regarding a specific, looking at which components, if I add in additive, how is that going to affect my overall combustion in a turbine? So with that, there's because this is so widely applicable between fuel design, emissions, engine design, there are several agencies and programs that, that have active calls for funding that I think this would be applicable to, or historically have had these types of calls. And then also I have a very large established collaborator and contact network. These are, a majority of these people actually have worked on experiments that have actually given me experimental data, or are willing to do experiments if I ask them to for particular conditions. And this is ranging from flames to reactors to shock tube ignition, actually doing full RCM type work and possibly even some engine experiments for me. So recap of the research part of this. We've looked at single component fuels, looking at something like morpholine, which is a novel biomass-derived kind of class of fuels. We're looking at how fuel nitrogen and fuel oxygen really impact combustion, what that means for things like emissions. And with that, we were able to identify areas where there are problems in the small molecule set. So moving down into the rabbit hole, looking at more and more niche type work. We looked at ethanol, fuel radical plus flame radical kinetics, and found that overall for low pressure flame situations, this class of kinetics is important and needs to be considered. And now looking towards the future, we're moving more towards larger real fuel systems, getting towards robust mechanisms that we can trust at conditions relevant to engines, high pressure where there's a lot of problems. Looking at things for real fuels and fuel mixtures so we can actually do some better design of engines and understanding better where our emissions are coming from. So developing surrogate models based off decomposition kinetics and the expansion of the small molecule set so we can move towards automatic mechanism generation and make this really cool tool that would be hugely valuable to industry if this could actually come together. And so with that, I'm going to briefly completely change topics and go to teaching philosophy. My approach is a little bit different looking from undergraduates to graduates. And so with undergraduates, your primary goal is to prepare them for a career, most likely in industry. And so you don't only just have to focus on those fundamental concepts, but really it's about getting active engagements, keeping your students involved, improving their oral and written communication skills, and giving them the confidence so that way when they do get to the end of the road in their undergraduate tenure, they have the confidence to go to a company and rely confidently on their own skill set. And so one of the biggest challenges I see with this particular subset of students is that many of them are coming from very educational backgrounds. You may have one student who's come from a private school who's had Calc 1 and 2 already, and this is a breeze, and the student right next to him may have come from a core school who doesn't even offer calculus. They've had geometry, and that's about it. And so being able to reach to different types of students and to be inclusive so you don't isolate a whole section of your class, to me, is one of the biggest challenges and primary focuses of my work, of my teaching work. For graduate students, really it's trying to teach them how to become independent researchers, to get them to really hone in on their problem-solving skills, to tackle something that no longer is there an answer directly in a textbook. You have to think creativity, you have to go do some independent analysis and expand upon the problems beyond what you would have as a problem set in the back of your textbook. And one of the biggest challenges, I think, with that is relating the course material to active research areas, especially for first-year graduate students. I know when I went to grad school, I didn't know what nanotechnology was. I didn't know what was out there for cellular type engineering and things like that. And all these projects were being offered, and I didn't know what to think of anything. So to be able to relate the fundamentals back to different active areas of research so students can understand when they're getting into the program where they want to go better, I think is important. And then lastly, a personal highlight of mine is, for teaching, is to promote diversity and inclusivity. As a female, I know what it's like to be the only female in a classroom. And so I think we're doing as a whole a great job of recruiting more and more women and minorities that go into STEM type fields. But the statistics show that a lot of students who graduate don't necessarily stay in those fields. And one of the biggest complaints that in surveys has shown that students who are women or minorities who feel alone and isolated, they don't get called on, they don't have a voice, and they eventually just kind of disappear. So keeping them actively engaged, offering to be a mentor, someone with an open door policy that they can go to and actively talk if they're having trouble or trying to find their own niche is something that's important to me. My personal skill set is strongly in the kinetics and reaction engineering side of things, thermodynamics, both classical and statistical mechanics, energy technology, combustion, computational modeling. So with that, I've identified a few classes that I could probably jump straight into between Introduction to Thermal Sciences, Energy Engineering, Thermodynamics, combustion, and others with just a little bit of preparation I should be able to teach without much trouble. So at least from a quick perusal of the course catalog, those are just a few of the courses that I identified. But in terms of possible new courses, one of the things that I remember as a grad school student, as I was just saying, is you jump into your first year of grad school and you don't necessarily know what's going on in research today. And I know since I've been in my postdoc, my postdoctoral position is at a Department of Energy lab. And with the Department of Energy lab, we're very conscious of national funding trends, and that really directs our research. So coming from grad school, where I worked on a project because my advisor said, you should do this, to all of a sudden having to think of how my research fits into a global scale and current policy trends was really kind of eye-opening. So I think it would be kind of neat to design a course where you look at the different trends and policies in engineering and science today, looking at different topics. So, I mean, my personal interest would be energy and catalysis and what the current policies and trends are in those types of areas. But you could expand and do maybe a couple weeks on different areas. Nanotechnology and materials, things like biomolecular and biomedical engineering. And with that, you can, especially for first-year graduate students, get a better idea of what's out there, what the possibilities are, where you might want to grow as a young researcher. The second course that I suggesting was one that kind of came up out of a conversation I had with another professor. We said that he kept getting the feedback that when he taught fundamentals to his undergraduate students, they just kept saying, even graduate students saying, well, I'm learning it now, I guess, to pass the course, but I'll learn the real story once I graduate or once I go into industry or research, that this is just a simplified problem, but the real story is once you graduate. And we all know that that's not the case. Like, those fundamentals are what drive all these different industries, and you have to know them well. So what I thought would be nice, especially for undergraduate students, is to look at areas of energy and environmental sciences, different technology, whether it's combustion to wind turbines, things like that, even nuclear type energy plants, and apply the fundamentals that you learn in mechanical engineering, whether it's thermodynamics, transport, fluid mechanics, and show how all of these fundamentals relate back to real world applications, with a focus mostly on energy and environmental sciences. We can even look into things such as like carbon capture and sequestration and really run the gamut, because these fundamentals still apply to all of those. And so with that, I'd like to wrap up. I have numerous collaborators who work directly on this particular set of research, but in particular I thank my primary PhD advisor, Phil Westmoreland, and my postdoctoral advisor, Raghu Subbaramakrishnan, and the numerous funding agencies that have sponsored me through my last, I guess, 9 years now. It seems like a long time. But with that, I'm happy to take any questions.
I missed the part at the beginning, maybe you already mentioned that, for example, this methodology for developing this kinetic modeling, how is the scalability in terms of, you have the cartoon for the field size and also about the conditions, you know,
Yeah.
and then how is that coming down the scalability?
Yeah, so, I mean, when you look at elementary kinetics, an elementary rate constant is the same no matter whether you're looking at a flame, a reactor, a high pressure engine. It should be the same. So I showed a little doodle earlier, this little, let's see if this works. No? Maybe?
Escape or you're trying to get out of it?
There it goes. It's on here.
There, start moving.
Okay. So the best thing we can do is we know these rate constants are the same no matter what. So we develop our models with that intent. I have a very heavy focus on trying to not only look at the problem at hand, but also to make sure we have the kinetics at high pressure correct. We have the low pressure fall off kinetics, so how that rate constant changes as or the branching between two different rate constants changes as a function of pressure. And so we assemble these into our models. and we validate against as much experiment as we can. So for our methanol model that we're doing, we are talking low pressure flames, flame speeds, but at elevated pressures too. I think we did a 15 atmosphere flame speed, which was incredible. Flow reactor data, shock tubes, looking at ignition at elevated pressure and low pressure. And we try to test as much as we can. And from that, where we see inconsistencies, especially if we see repeating inconsistencies, that tells us there's something wrong there. So in that case, we found hydroxymethyl and methoxy, these two species that are very important in methanol combustion, and just combustion as a whole. Something seemed wrong there. It didn't seem right. And those are reactions that had been estimated and tuned through the years in the literature. So we did a theoretical analysis on that to really get that chemistry correct with the best methods we have today, and input that back in the model. And then we got much better convergence, at least in those areas. And so that's kind of and once we can say we can do high pressure ignition, low pressure speciation, high pressure speciation in flow reactors, and all of these things together, then we can more reliably say this is going to behave appropriately in an engine condition, even though we can't do the fundamental tests that we can do in these isolated experiments.
So another curious question is that earlier you mentioned, we talked about earlier today, so your methodology is more, you work a lot with Professor Dreyer in Princeton University, and also we talked a little bit about the methodology with Westbrook from Lawrence Livermore Lab, for example. So fundamentally, are they doing this different methodology, or just for particular use? And is there any conflicts in this type of, because this is kind of like interesting that they seem to take a different approach.
Yes, there's very different philosophies, and so like the Charlie Westbrook school of thought is, well, we know in general, like this primary hydrocarbon, this primary CH bond reacts about this rate constant. So for all of those reactions, we are assigning a specific rate constant. And then, sometimes even go so far as to say, well, these radicals are similar, we're gonna lump them into one species. And because of this oversimplification, this overestimation reliance, they tune their model specifically for something like an ignition. So because of that, you end up throwing out so much chemistry, and you're not able to then take that model and look at things like speciation, or like, which leads to things like emissions, or to really get trends on fuel breakdown chemistry, like how that, what components of fuel really drive combustion, make it, react, like ignite at lower temperatures and things like that. So you lose a whole ton of valuable information that way. And so I try to keep things as...
Right, so for example, for me, like a CFD modeling, like when I choose these models, and it's, you see the fundamentally the different approach, and it's, do you kind of get up to us, the use with cautions, or is there any predominant approach there?
I mean, for what's out there today, I'd say if their model isn't designed, say it's specific for something, don't use it. Because a lot of people take these and heptane models for diesel, and they're tuned for ignition, and now they're trying to figure out why they can't predict what comes out of an engine tailpipe using it. It's because the chemistry is just not there. So that's one thing I think is, don't go beyond what's being sold.
So now I'll get a little more specific.
Sure.
So one of the things that you talked about was high pressure natural gas mechanism as an area that needs work. So we use Henry Curran's natural gas mechanism, which we think is our best.
Publicly available, I would agree.
Yeah. So what's wrong with it?
They're another.
That was going to be my question. No. So what do you think?
The group does really good work in trying to make something that is applicable to a lot of engineering things. The problem, again, with them is they've, in my opinion, overtuned. And so there are some specific examples where we know for specific rate constants in their mechanism, they've overtuned so much that it explains why sometimes when you go to high pressure, you're not getting the correct kinetics. They've put too much reliance, I believe, on the experimental data where they try to run directly through it. I try to take the approach of let's figure out the theoretical chemistry and everything within their uncertainty bounds, and if it's not perfect, that's okay. There might be something missing, and that's...
So is what you learned working on methanol, I mean, is that kind of informed that there might be something wrong?
Oh yeah, I mean, I kind of alluded to small molecule dynamics. We found for HCO, there's a quantum effect that up until now, even in fields other than combustion, everyone said, don't worry about it. It is a completely minor process. At most, it's going to have a 1% effect if you're not worth looking into. And so me and a small group of people with some of the best theoretical kineticists out there, we derived what the actual probability for dissociation based off this quantum effect is. And then I developed a code where we can apply this probability dissociation to every reaction with HCO and put it in any mechanism. We did do Henry's mechanism. And what you end up seeing is just for methane combustion, flame speeds increased by, I think it was 14% for flame speeds. And the speciation changes. You end up seeing prompt formation of radicals, so that changes your whole combustion dynamics. So by tuning, they've clouded out all of that. And so getting at the better kinetics means that now you can add to that mechanism and rely on it. So if you take their natural gas combustion mechanism and add ethanol chemistry over it, they don't match, and that's because it's been over-parameterized.
From a teaching perspective, it looks like you've got plenty of background to cover a lot of different courses, but if
Yes.
you had to select one that you could really take to be like your first course to teach and focus on, what would you do?
I know it's his baby, but I want to do combustion.
Well, have I got a deal for you?
Everybody, we share our classes.
That and thermodynamics. I especially love the difference between classical and statistical thermodynamics. I know much more the emphasis in mechanical engineering is the classical side of things, but StatMech is still really cool. So, yeah.
I have a question about rate constants. With the Arrhenius equation, there's a whole thicket of different forms of it.
E is modified where it's typically A times T to the N times exponent E over RT minus E over RT. That's our typical standard, but that does not incorporate pressure dependence and things like that.
Exactly.
So we use things like P logs, which is basically a set of Arrhenius expressions at specific pressures, or something we could fit them sometimes to TROA formats where you have a high pressure rate constant, like a K infinity, K0, and then the pressure dependence in between.
Okay.
So yeah, there's a host of different formats.
Yeah, there is. I mean, so even the word rate constant is wrong.
Yeah, no, it's not a constant by any means. Yes. And then there are some errors just associated with fitting those damn things because they don't necessarily follow how, they don't fit well sometimes.
I think you mentioned at some point about those codes that used to generate mechanisms.
Yes.
And I used one of them, the one from Professor Green at MIT.
Oh yeah, reaction mechanism generator.
Yeah, how do they work? It seems so like a black box to me because you just give it the fuel and an oxidizer and then it generates a mechanism automatically no matter what
Yeah.
fuel and what's
So,
the process there?
I'm good buddies with Richard West, who is the primary developer of React. We've had, especially when I was doing my PhD in MIT, it was just up the road. We had many a conversation over a cup of coffee over it. So basically, there's this idea of group additivity. So each different non-hydrogen atoms, depending on what it's bonded to, has a different contribution to things like enthalpy, entropy, and then from that, you can estimate the reactivity of those particular sites. So what it ends up doing is basically figuring out through a whole class of reactions, whether it's internal abstractions, external extractions, isomerizations, decompositions, and there's a whole series of them, one by one, that goes through every possibility, estimates that rate constant, and then what it does is it looks at the relative rate constants for each of those and says whether something's too slow to worry about, and then eliminates it. And that's basically the short story of how they do it.
All right, Gary? Yeah.